In this video, we're going to look at some different models of computation and see how those different models affect the running time of algorithms. First, we'll look at using a Turing machine that has multiple tapes, and we'll find out that that can speed things up quite a bit. It can be a factor of n squared faster, so that's important. Then we'll look at non-determinism, and we'll see that allowing a non-deterministic Turing machine gives us vastly greater power. So we'll look at these two different models of computation and see how the running time is affected. Let's start by asking about a model of computation where our Turing machine now has multiple tapes instead of just a single tape. We'll look at the same problem that we looked at in the last video, which is to determine whether the input has the form 0 to the k, 1 to the k. In other words, is the input a string of zeros and ones, the zeros precede the ones, and they're the same number of zeros as there are ones. Let's look at an algorithm that uses a Turing machine with two tapes. And I'm not going to give the algorithm very formally, but instead I'm going to just sort of sketch it out here, and then that will allow us to analyze its running time. So initially, we have our input on the first tape, and we have a second tape that's blank. So the first thing we do will be to scan the tape and copy, as we scan, all the zeros to the second tape. And then when we hit the first one, we'll stop. Then we reposition our tape head on the second tape to the left end, as shown here. And then we'll scan both tapes, and as we scan, we'll make sure that the head on the first tape sees a 1, and the head on the second tape sees a 0. And the heads will move together through the 1s here and through the 0s here. And if this is a valid input, the heads will reach the last symbol at the same time. And then the last thing we need to do is make sure that both tape heads hit the blank at the same time. So now let's analyze this for the running time. To copy all the zeros, we have to scan half the input. And so that takes n over 2, which is order n time. Then we reposition to the beginning, and assuming this is a valid input, that's again n over 2 time. So it's linear, order n time to reposition. And then we scan both tapes simultaneously, in making sure that they both hit the blank symbol at the same time. So as we scan through the zeros and through the ones, we have to go through n over 2 transitions. So that's again order n time. So all in all, we have order n, and order n. This machine takes order n time. And remember that last time, in the last video, I said with a Turing machine using a single tape, this algorithm takes order n log n time. So here we've gotten an algorithm that is faster, but it's because we're using a different model of computation. So having a multi-tape Turing machine allows your algorithm to be done faster in many cases. And here's a theorem that shows that you can execute the same algorithm on a single tape machine, but it's going to take longer. And this theorem talks about how much longer. For every multi-tape Turing machine algorithm that takes time t, there's an equivalent single tape Turing machine that takes order t squared. So we can simulate a multi-tape Turing machine on a single tape Turing machine, but the simulation may take t squared time. And so let's look at the proof of this. Basically, it has to do just with the length of the longest tape on the multi-tape machine can be. Well, in time t sub n, the running time of the multi-tape Turing machine, which has several tapes, the longest the tapes can get to be is the number of steps that have been executed. Because in order to write something onto the tape, it takes one step, so the tapes can't be any longer than t. Okay? Now you can simulate that multi-tape algorithm on a machine with only a single tape. However, each step of the simulation takes a long time. And in particular, it's proportional to the length of the tape. We're going to have to simulate, we're going to have to scan those tapes, and in order to scan those tapes, and we've got to look through possibly all of the tapes, and figure out what we're going to do in the single tape Turing machine, and that takes time that is relative to the length of the tapes, so order t, time. So the algorithm itself takes t time, and the simulations of each step take order t time, so the result is order t squared time. So the bottom line is that the model of computation matters. The thing to remember here is that the actual computer you're using can make a difference. But it's also important to understand that the differences between one machine and another machine are, shall we say, relatively small. And in particular, an algorithm that takes polynomial time will remain a polynomial time, regardless of the details of the model of computation. Now, if you move to a faster microprocessor, you might be going at twice the speed, or even 3 or 4 times the speed, but that's a constant speed up. And in some cases, like moving from a single tape Turing machine to a multi-tape Turing machine, you might get a speed up of n squared. The single tape algorithm might take as much as n squared time relative to the time taken by the multi-tape machine, but those are still polynomial. Okay, so these are polynomial time differences, which we will consider to be relatively small, at least when we look at non-deterministic machines. So as long as the machines are deterministic, all the different models of computation are pretty much the same. They may differ in terms of being different polynomials, but they're still in the class of polynomial time algorithms. The class of algorithms that can be executed in polynomial time is quite robust. Okay? The actual details of the model of computation don't matter. It doesn't matter really whether you're doing it on a single tape machine or a multi-tape machine, whether you're using an old Intel 8080 microprocessor or you upgrade to the latest Intel chip. Those are constant factor speedups. So the class of algorithms that can be executed in polynomial time is a robust, well-defined class. The thing is, we're looking at deterministic machines here, and next we want to move into non-determinism. I defined what running time is for deterministic Turing machines as simply the number of steps that the Turing machine takes. We need to define the running time for non-deterministic Turing machines as well, and we define the running time of a non-deterministic Turing machine as the number of steps that the Turing machine uses on the longest branch of computation. So remember, we're talking about decidable algorithms, which means that all branches of the computation terminate, and we care about the longest branch of the computation. So in this picture on the left, we're showing a deterministic computation history. And there's only one choice at every step, and we end at accept or reject. Over on the right-hand side, we're looking at a non-deterministic computation. Now, in this particular case, one of the branches ends in accept at this point. And so you might think that the running time should just be the length of the branch to accept, because once we know there is an accept branch, this machine accepts. So that's not the case. We have to let all branches terminate, and even though some branches may take longer, we measure the running time as the length of the longest branch in the computation history. Earlier we showed that a non-deterministic Turing machine can be simulated on a deterministic Turing machine. Well, every non-deterministic Turing machine can be simulated on a deterministic Turing machine, but it may require, in general, exponentially many more steps. Okay, so it's going to require, in general, a lot more steps. Just to put an example on some numbers as an example, imagine that the non-deterministic Turing machine takes 419 steps on some given input. The deterministic simulation can always be done, but the number of steps might be 2 to the 419th. If every step in the computation has only two choices, has exactly two choices, two non-deterministic choices, then this tree of possible branches grows, and it grows by a factor of 2 at every step. So after 419 steps, there are 2 to the 419th different branches, which is, of course, an absolutely huge number. So here I'm saying the same thing. If, for example, the non-deterministic Turing machine can perform an algorithm in n² time, then the deterministic simulation can be done in an exponential, where the exponent is that n². So we can do this simulation on a deterministic machine, but it requires vastly many more steps. And by vastly, I mean exponentially many more steps.